This is basically a geo-intelligence problem. I support basically the Air Force in doing a lot of their problems, but I also support private organizations that do work on watersheds. But the problem is fundamentally a naval intelligence problem, and the Navy basically has a very serious need for predictive and diagnostic operational models for understanding the relationship between that which you can image on the surface and that which you can measure on the bottom. So this work is basically can be reduced to this cup of water. How does basically what you see on the surface of the water relate to what you see below it? The Bayesian belief networks allow for joint probability density function characterization of the nonlinear interrelationships in the fluid. Turbulence, very, very nonlinear, just like your stock markets and all your crazy consumer dynamics that people have been looking at. Success in model use for this small scale DNS range, because we're looking at a DNS cube in the order of centimeters. But we want to be able to say that if we can understand how water works at a small scale, then we can probably use the same idea and extrapolate it to large scale. So numerically simulated analysis, data analysis on small scale water phenomena, and then see if that can give us understanding of how to treat water at the large scale. And at the large scale, what we're imaging, we're using MSI, HSI, hyperspectral imagery, multispectral imagery. So using DNS as a proxy for basically MSI or large scale measurements. The long-term goal, again, is the large-scale stuff. That's what the Navy cares about. That's what a lot of watershed organizations care about. Basically being able to understand the relationships between different water masses which are distributed over an area, such as United States, but it can be in other areas that the Navy is also interested in particular, like overseas. Again, how can the connections between the spatially separated water masses be parameterized using Bayesian belief networks to understand how a watershed behaves as a system? Again, DNS is being used as a proxy for MSI and HSI. Both of them are three-dimensional entities. So we're trying to see if we can gain insight into the MSI and HSI analysis methods by using DNS. DNS deals with, of course, with the uncertainty surrounding hydrodynamic flow variable propositions. And for us, for this talk, the hydrodynamic flow variable propositions are the surface spatial scales, again, what happens at the surface, and then what happens below. So surface spatial scales and subsurface dynamics or stress. And the first part of this analysis is basically really a tour de force of machine learning. So before we even do the modeling, we need to create features that the BBN can understand, and we do that by using machine learning. Again, the model that I'm using by no means close to the complicated models that people have already shown. It's a naive Bayesian belief network. Again, we're starting simple, trying to show people how you should approach the problem, and then later on adding on the complexities. Again, we're dealing with pressure scales, concentration scales, vertical velocity scales at the surface, stress at the bottom, and then a sinusoidal pressure gradient or stress that's basically stressing the water. So basically think of this water as being stressed by a pressure gradient back and forth. And then ask yourself, how does the surface relate to the bottom? Again, the modeling goal, understanding the interrelationships between the two. This approach very different from what people in the coastal modeling community actually do. They're usually doing forward modeling, using a forward theory. So they're basically taking initial conditions, taking a quantitative model, maybe numerical, kicking it, and they get predictions. We're going the opposite way. We're taking observations, using a quantitative model, in this case the BBN, and then see what sort of estimates it can give us, what sort of insight it can give us into our problem. Again, HSI, MSI, IR, DNS, whatever the data is on the right-hand side, and see if it could give us any sort of helpful intelligence decisions on the left-hand side. DNS data is nothing but a cube. XY, basically X, Y, and Z, and for every pixel or subunit within the cube, you have basically pressure, velocity, and all the other derivable variables. Extremely small cube on the order of centimeters, 10 centimeters, 5.4 centimeters, 10.6 centimeters. Think of it again, if this is the cube, a sinusoidal pressure gradient is basically being pushed through it. And it's basically the wave, the pressure wave is like about 5.6 meters in wavelength. Reynolds number, don't worry about it, just means that it's turbulent. That's all you need to know about that. All you need to know is that this is basically a cube. Stress it periodically, back and forth, back and forth. Tell me what you see. How does the top relate to the bottom? That's the question. And it has basically dirt in it. That's the other only caveat. You have dirt particles in the water. We're dealing with 22 wave cycles, 3 phases per wave cycle, and we're looking particularly at maximum velocity, minimum velocity, and zero velocity. And again, we're looking at the vertical velocity, concentration, pressure fields at those 3 phases. In order, the first part of our analysis basically to peel off scales, physical spatial scales associated with the surface of the water, physical pressure scales, velocity scales, concentration scales at the top. In order to do that, we have to use machine learning to basically pull out that scale information. So first part, scale information analysis, scale extraction. We use the SOM, ICA, and some other techniques. SOM, for all of you who don't know, is basically taking the skin layer of the fluid, the depth structure of the skin layer of the fluid, and feeding it to like this neural, almost like a neural network. And what will happen is that the network, as you feed the SOM network information, it perturbs every time you feed it until it basically becomes set. When that SOM network becomes set, which is like there, that's basically has all the information about your coherent scale. So you take this information, feed it, which is basically this, basically concentration, velocity, and pressure, velocity, depth profiles in the surface of the water. Feed it to the SOM network, and the SOM basically membrane will perturb. After a while, it settles down to a set state, and it's able to give you the coherent velocity structures within the fluid, or the pressure structures, or whatever structure you're interested in. For us, pressure, concentration, velocity. Again, surface information. So that's one analysis that we use to pull out scale information. Another analysis that we use is ICA. It's a way of basically separating your data into Gaussian and non-Gaussian parts, independent components for you who I'm sure know about this analysis. Again, taking the skin layer of your water, feeding it, and basically feeding it to the ICA algorithm, and then pulling out that part which is non-Gaussian, distinctive or independent of the Gaussian fluctuations. Or something. Got you. Got you. Just pulling out basically the independent or non-Gaussian part of the fluid. So again, just both of these methods are just basically ways of pulling out coherent, cohesive structures in the surface layer for pressure, concentration, velocity. That's all it is. Once you do the SOM, the ICA, you can also perform next a wavelet analysis. This is the thing that actually pulls out, the scale information. Won't go into all the details of it, just suffice to say that if you go through it, you'll be able to pull out characteristic scales from this entity called the scaleogram. So we proceeded from SOM and ICA. We used both, basically the wavelet analysis on both of them, and from that we can pull out characteristic scales for pressure, velocity, concentration. That's all the machine learning is doing for the surface layer. So we have physical scales for the pressure, velocity, and concentration for the top layer. We basically also calculate the stress in the bottom layer. So pressure, velocity, concentration, top layer, stress in the bottom. And that's basically all we need to go to the next step. So this is basically plotting the stress scale distributions, relating, again, how the water behaves below the surface with how it behaves at the top for different phases of the pressure gradient. So this is basically what the vertical velocity SOM scales look like. And basically you'll find a consistency throughout all this analysis. For the zero velocity phase, that means the water just basically ambient, sitting there, no stress being placed on it. You'll find that the stress bandwidth is narrow, the scale bandwidth is quite large. So basically no pressure gradient being really placed on a fluid. You'll find that your stress bandwidth is very, very narrow, but your scale bandwidth is very large. On the other hand, at the max and min phase, the stress is the opposite. Stress bandwidth is broad, scale bandwidth is very narrow. Makes sense. Everybody takes their morning coffee, you stir it up. Little do you know that if you were to look at it, if you were able to put a dye tracer in your coffee, you'll be able to see these very worm-like eddy structures at the very, very small scale. That's basically what you see at the max and min phase. You see basically this broad bandwidth, this very narrow bandwidth of scales. Stress bandwidth is broad, scale bandwidth is very narrow. It's consistent again with how turbulence behaves. As you stir your coffee, you produce these very, very small eddy structures, and they're basically, the bandwidth is not very, very large. Actually, the scale bandwidth is pretty narrow. The stress bandwidth is very, very large. At the zero phase is the opposite. Pressure has the same structure. Again, stress bandwidth at the zero phase, no stress. Stress bandwidth is very, very narrow. Scale bandwidth is very broad. Max and min phase, that's when you're exerting stress on it. Stress bandwidth is broad. That means all the eddies feel a distribution of stress values. Scale bandwidth is very narrow. The scales, the turbulent scales, are very, very small, pretty narrow. No bandwidth to them. Again, as you stir your coffee, you produce these pressure worms also, and they're all pretty small. Sediment concentration is different. It doesn't exhibit that narrow, broad structure because it's kinematic. It's not dynamic. So what's happening is that even when you stress the fluid, the sediment particles bump into each other and they basically coagulate. And so you basically have this cohesive coagulation of all the sediment particles that gives it a very broad spectrum, very different from pressure and velocity. So again, something that's verified by numerical models. Velocity, pressure are dynamic, so they behave as you would expect from the Navier-Stokes equation. Sediment concentration is kinematic. It reacts to whatever happens, almost like a fly moving around in a room and bumps into another fly, or dirt moving around, just particles moving around, bumping into each other, and then they will basically stick to each other and then move away, and stick to each other and move away. Not basically, it's a kinematic effect, not a dynamic effect. So we have the scale information, so what? Now we're ready to put it into the Bayesian belief network. Again, conditional probabilities and all that sort of thing. Again, we have stress in the bottom layer, pressure, concentration, vertical velocity in the top layer. Just basically details of the Bayesian belief network. The pressure, the concentration, the vertical velocity from a scientific or a Judea-Pearl mentality, those are effects. The stress is the cause. It's not really that way. In turbulence, there is no stress, there is no cause and effect. Everything happens at once. We use these Bayesian belief models only so that we can help ourselves understand what's going on. But I want to make it clear that turbulence does not behave like cause and effect. Everything happens at the same time. There is no why did this happen, because you'll basically keep chasing your tail like the serpent chasing its tail. But these models could be useful for helping us understand dynamically what's going on. Again, we're using a naive Bayesian belief network. We're postulating that the pressure, the concentration, the vertical velocity are independently related to the stress. It's not true at all, but we just use this as a way to understand what's going on. As a first order model, again, the effect nodes are D-separated. You know what that means already from your study of Bayesian belief networks. This is just details as to how we broke up the causal information and effect information into basically four intervals of basically a 4-level gradation range for the causal node stress, and then a 5 gradation range for basically the effects. And again, we're looking at the relationship between physical scale size at the surface and stress at the bottom. Again, to remind people, why is this important? The Navy can only see things at the surface. It can only look at scale. It's a two-dimensional surface, so the only thing that makes sense is physical scale. So we're trying to figure out if we can look at physical scale at the top, how is that related to what's going on in the bottom? In other words, stress. Again, we're looking at conditional probabilities, the probability of a surface feature, spatial scale size as the effect node, conditioned on the stress level at the causal node or the subsurface feature. So it's always surface and subsurface. And so I'm just going to show you some of the results of our analysis. This is the initial marginal probability distribution. No instantiation at all. It's almost like steady state. Stress has a Gaussian distribution, which you would expect from the back and forth action of the pressure gradient. Concentration, vertical velocity, and pressure are all skewed towards small scales. Makes sense also because as mixing goes back and forth in the mean, it's going to most likely be dominated by small scales. So nothing really truly surprising there. First simulation, diagnostic analysis, reasoning from effect to cause, reasoning from the surface to what's going on beneath the surface. So we instantiate concentration at the range of 3 to 4 centimeters. And we basically watch how the Bayesian belief network, naive Bayesian belief network behaves. And we found something that was interesting to me. The stress was not partitioned into any one unique interval. That means, what I mean by that is that diagnostically speaking, the allocation of stress to specific intervals from the surface concentration field may not be possible. What that means is that when you instantiate concentration, we were hoping that that the stress basically was partitioned only in one interval, but it wasn't. It was spread out in both positive and negative. So it makes it so that it becomes hard to readily, uniquely say what particular stress is going to happen, because both of them happen quite equally. Just from looking at the concentration, of course. Prognostic analysis, reasoning from cause to effect. We instantiate stress at -2 to 0.5 pascals, and then again watch how the Bayesian belief network behaves. For large negative instantiation, we get these very, very small scales, which is fine. But when we basically go to, again, prognostic analysis of 0.5 to 2.2 pascals, prognostic analysis, large positive stress instantiation produces much larger concentration scales. What this means, practically speaking, is that from a naval intelligence perspective, if you want to, naval sensors can sense large scales better than small scales. So their sensor is going to most likely be able to pick up stress that's positive rather than negative. So I go to my leadership and I say I have an enemy in the water and it's going into a tidal inlet and I want to be able to detect them. Should I be looking when the tide is going in, positive, or when the tide is going out, negative? You should be looking when the tide is going in, because that's when your structure would be most visible. It's not that structures are not there when it's coming out, but from the perspective of a sensor, sensors are more, they have a preference for being able to pick out the large scale structures. So you should probably look at that time when the tide is going in. Again, the tide being like a pressure gradient. Again, has implications for remote sensing of MSI and HSI. So conclusions, was able to show successful feature scale distillation for DNS cubes using the SOM, ICA, and the two-dimensional Morley wavelet analysis. Feature information that comes from the analysis can be fed to a naive BBN and used to perform statistical analysis or inference for the presentation to leadership. What's important here is that we've come up with at least a rudimentary geo-intelligence formalism, which can actually be used in the future to systematically understand, again, the interaction between what happens at the surface and what happens below the surface. Again, it has implications for use with MSI and HSI systems, multispectral and hyperspectral imaging systems. For the future, we're looking into hidden Markov and Bayesian neural network system modeling for boundary layer dynamics. The question being, can the Bayesian perspective be used to improve our mapping between, again, the surface and the subsurface? And then extending what we've had from the small scale to a much broader array of water masses. Again, as I talked about, as the long-range goal. And this is collaborative work that we're doing with the National Great Rivers Research and Education Center. Again, being able to say, can Bayesian belief networks understand the relationship between different water masses over the Mississippi? Everybody's dumping their products into the Mississippi River. People go to basically Congress. We want money to help clean up the rivers. And we don't penalize for anybody else's problem. Kentucky says, it's not us, it's Ohio, because we can show in the Bayesian belief network, when they dump, it goes crazy. Illinois says, nah, it's not us. We did the analysis. Our impact is very, very negligible, if anything. It's being able to do that sort of thing really starts with the Bayesian belief networks, being able to influence environmental policy. That's it. If there's any questions, I'll take them.